Hello everyone. Today in this section we are going to talk about the Save Cube. What is a Save Cube? Why do we use the Save Cube? When do we use it? And hopefully you will have a bit more insight in that product as well when we have finished this section here. Okay, so we are calling this Save Cube, as many of our electric systems has different names, and a cube, because it's a short for a cubicle. Everything is within one cubicle. That is not only the only one benefit. I will tell you a bit more about that. Let us put up a typical diesel electric system with 4 diesel gensets, many vessels within offshore, yacht, mega yacht, cruise, with a diesel electric setup will have 4 gensets like this. You may have 3 or 5 or 6 or 7 or 8 in big vessels maybe, but very typically 4. So we start with that. If you would like to know why we have a diesel electric system compared to a diesel mechanic system, I can advise you to one of the other sections that we have, where we discuss why hybrid electric mechanic. So have a look at that, so you have a bit more insight in why we are choosing an electric system. But today we're talking about the cube, and I will then start with a diesel electric system. First, I would like to draw for you a standard diesel electric system as it is on many, maybe the majority of the diesel electric vessels out there. So when I'm drawing this is not a cube. I will draw a standard typical system first to explain the difference. So what I'm drawing now is in fact what we call a save line. We call it a save line because it's a streamlined delivery, it's a streamlined production engineering. It's something we have done in many years. It's a very typical normal diesel electric system. So I will first start to draw a save line, a typical system. And for a save line, we may have some main propulsion frequency drives, and we may have maybe some tunnel thruster or azimuthing thruster drives. Let's say this particular vessel has 2 main propulsion propellers and 2 tunnel thruster propellers. So on all these we have an electric motor, and of course if you have a permanent magnet tunnel thruster, then the electric motor is a part of the propeller itself, but it's still an electric motor. So I will just draw it like this, even though it's a pod, it's a AC pull, or it's a permanent magnet azimut. If they are in a diesel electric system, all of these, they have of course the electric motor on. So just for indication, I draw all the motors like this, with a shaft between the motor and the propeller. And we would like to be able to regulate the RPM of the propeller. Hence, we have to regulate the RPM of the electric motor. And to be able to do that, we need a frequency drive, because we need to adjust the frequency to the motor. That we have touched in some of the other sections. So please have a look at one of them. And we have cables. I'm now drawing the cables between the switchboard and each frequency drive. So this is a frequency drive, this is a frequency drive, this is a frequency drive, and this as well. We connect the generators to the switchboard. These generators are providing the power for the switchboard, and the switchboard is supplying the hotel, all the load on the hotel, and as well the power for each and every propeller on the vessel. So you will see that I have made 4 frequency drives based on active front-end technology, as we have touched in another section. Because I do not have any transformer in front here. So inside these frequency drives, there is a rectifier, a DC bus, and an inverter. That you will have inside all of these, DC and inverter. So rectifier, inverter, rectifier, inverter, rectifier, inverter, and DC plus and minus in between. So that is an active front end. It's not a 12 pulse, it's not a 1824 pulse. We do not have any transformer, and the power may flow in both directions through this frequency drive. So this is not a save cube. This is a save line, a typical diesel electric system on board many vessels. On the switchboard, we need to have 60 Hertz. The voltage need to have 60 Hertz. So we need a stable frequency on the voltage on the switchboard due to everything that is connected to the switchboard. And that is the reason why we need a frequency drive, because we want to regulate the speed on the propeller. So we need 0 to 60 Hertz, 0 to 60 Hertz, 0 to 60 Hertz, and 0 to 60 Hertz. So all these frequency drives will be able to regulate the RPM on each propeller. And to be able to have 60 Hertz stable on the switchboard, you need to have stable RPM on all the generators, and of course on all the engines. So to be able to have 60 Hertz constant on the switchboard, we need to have, let's say this is a high-speed engine. We need to have stable 1800 RPM for a high-speed engine on all the engines. So they need to be stable, running at constant speed, fixed speed throughout when they are in duty. Okay, we have in another session discussed why we would like to adjust the RPM freely on the propellers. That is due to the propeller losses. There is a huge saving in regulate the RPM down to a lower RPM when you need lower thrust. So if you are not running or sailing your vessel, if you're not sailing your vessel at full speed ahead, but you are adjusting the speed of the vessel down, well, then immediately you can save fuel from regulate the RPM on the propeller down. Because if you can take away a couple of 100 kilowatts, maybe in the area of megawatts of losses for a big vessel, if you take away megawatt of losses from the propeller side, you will of course save megawatt production, because you do not need to produce all those losses. If we had fixed speed here, if we had just a starter and fixed speed, then we had to produce the propeller losses from the engines. So again, to one of the other sessions, we have already explained that savings over here. However, we have discussed in the HSG session around savings on the engine side if we can do something about the fixed speed on the engine. If we are able to lower the speed of the engine in low load conditions, then we can save fuel. You know, the reason why we have many engines in a diesel electric system is that you are able to stop and start engines based on load. So you start with one engine. Do you need more power down here? You start the next engine. If you need further more power, you start the next engine, and so on. That gives you the opportunity to run the engines more close to the optimum, because it's better for the engine, it's better for the fuel consumption to be close to 100% load. It's better than be at 20% load. The challenge occurs at once you have safety regulations, requirements for the utilization of the vessel, and those regulations say that you are not allowed to run with only one engine. So in that case you need to run with 2 or more engines due to safety backup reasons. In case 1 or 2 engines stops, then you need to have something already running and ready to take over. In cases like that, you will have engines maybe running at a very low load, maybe as low as 20% load, on each engine because they have to run due to regulations or safety reasons. If it is a DP operation or a redundant propulsion class, so you need to look into the class rules and see, have a look at the redundant propulsion requirements and the DP requirements. Anyway, then we are looking at the system. Is it possible to make the life easier for the engine by let the engine run at variable speed? Because in cases where you have a 20-30% load on the engine, it would be very good if we could reduce the RPM, keep the combustion heat, and have a more optimum combustion in the engine and save fuel. Well, that is possible by doing something with the electric system. Okay? So then I am moving all the frequency drives inside one cabinet. And that is what we are calling a save cube. In fact, it's the same components, but we are moving them into one cabinet. So what we do, you are now familiar with the active front-end frequency drive, if you have had a look at the other sessions, and you understand that we need a rectifier. And from the rectifier, we are producing DC, not AC. So we still have AC coming from each and every generator into the rectifiers, and the rectifiers, they are producing DC, plus and minus. So inside the cube we have distributed DC, or as some of our competitors call it, a DC grid. This is more or less the same we are doing here. And then we of course need the inverter to be able to make an AC with frequency that we can adjust. So we need an inverter for this propeller, we need an inverter for this propeller, an inverter for this, and an inverter for this. And those are connected to the DC and are making the AC with the frequency we would like to have. So you can see that we have moved the frequency drive, we had it here, we have moved it inside into one cubicle, or in short, cube, save cube. Suddenly, we do not have 60 Hertz inside the switchboard. We have DC inside the switchboard, direct current, 0 Hertz, that's DC. So, okay, suddenly all our engines are disconnected from the requirement of having stable and fixed RPM. So suddenly all these engines can now run from idling maybe 600 RPM to 1800. So by this move we have released the engines from the fixed RPM requirement and letting them run freely in RPM. So when we need low load, we can as well take down and regulate down the RPM to the most optimum running point, working point for the engine at this particular load. So basically this is the Save Cube. The Save Cube gives you possible variable speed on the main engine. Okay, you have fuel saving. You have several more additional benefits from that. You will of course have a more clean and hot combustion. The mean cylinder pressure will be a bit higher, so it will be warmer inside the piston and the combustion. So your exhaust will be warmer, and your cleaning system, if you have that in your exhaust, will as well perform better. In addition, for a yacht maybe, or a cruise vessel, you will in many cases have been able to regulate down the RPM, and then your vibrations and your noise coming from the engine will as well be reduced. So that is an added benefit from the Save Cube. You're then able to take down the noise and the vibration from these components as well. Couple of more small benefits. In the Save line where we had the frequency drives distributed here, you need to have water cooling to each and every of them. With this solution, you have water cooling only to this cabinet. So the fresh water system is a bit more easy because you connect it only to this cabinet. And last, all the interface, the signal cables going between the frequency drive and the switchboard, all the signals that you have to connect and do the cabling on board the vessel will not be there anymore, because all those signal cables will now be produced inside. They will be put inside the cube and ready installed in our factory. So it gives you a bit more small benefits in addition to the fuel saving part in low load conditions. Okay, then the question may be from you, can we utilize this for a hybrid vessel or a mechanic vessel? Yes, of course we can, and we have already sold to some customers hybrid vessels with a Save Cube. And I can make a quick indication of that. We have typically mechanical installation with a gearbox connected to the shaft generator, and then you suddenly have a generator motor here, and this generator motor, it will work as a generator, it can work as a motor, you may boost, you may drive full electric by stopping the big engine, and you have all the flexibility that we discussed in the HSG section. So suddenly you have a hybrid installation with the HSG functionality, but connected to a cube. And very typical, this is a twin screw solution with two main propulsion propellers, and I have to move the generator a bit. So, and this is then again a generator and motor. Suddenly you have a hybrid solution ready to be promoted and designed into a vessel where I would like to have mechanical transmission as well as full electric if we stop the main engine, and boost if both of them are working. And in addition, you have still the same functionality of variable speed of the main engine, because you do not have to produce fixed frequency from the generator due to the fact that you are connected to this DC bus inside the Save Cube. So with this, you have a Save Cube for a hybrid installation or for a full electric, as we discussed. Just one thing before we stop. It is important to remember when you have a solution like this that you still need hotel load. And all the hotel load will have to go through this DC distribution, because all your power is produced by these generators and will be rectified. So you need an inverter to make your switchboard for the hotel load and to have a stable 230 volt, maybe 50 hertz. You can pick and choose whatever frequency you would like to have, 60 or 50, because we have an inverter, so we produce the frequency and the voltage you would like to have out on the hotel load. So by that, you have a quick and short introduction to the Save Cube. What are the benefits from the fuel savings on the engines? And again, have a look at the diagram of an engine, and you will see on this diagram that if you reduce the RPM when you are at reduced load situations, you will be in a better performance when it comes to fuel consumption. So please have a look at that so you can have an understanding. I'm pretty sure you will have good help from our engines specialists if you ask them for a diagram of the fuel consumption combined with the RPM and the load. So by that, hope you understand a bit more about the product, the system, the Save Cube system. Thank you.